We've got everything done on the game, but we need a way to configure it externally, not just in code. There are 13 total bits of configuration data, but there are only 4 I/O pins left. We're going to need to serialize our configuration switches and suck them into an internal register. For hardware, I'll feed DIP switches into two 74HC165 parallel to serial shift registers connected in series. These will run on 3.3 volts, so we can attach the serial output directly to a GPIO pin without a level shifter. We could just run the one feeding the FPGA on 3.3 volt and the other on 5 to save 3.3 volt current, but these only consume about 100 microamps each, so no need for wacky stuff. The light 10K switch pull-up resistors will consume about 25 times that at a total draw of about 5 milliamps, way under the 200 milliamp user allowance for the onboard 3.3 volt regulator. We'll use 3 GPIO ports for this: serial load, serial clock, and serial data in. Naturally, we'll start by adding those to the PCF file. And then add those to main. The 165s have 2 sections, a data in latch and a serializer. For timing, we'll use our 1 millisecond clock since we have it laying around, and we'll use that to step a 5-bit phase counter. We then use the phase state to control the serial I/O. Internally, we'll need a 16-bit register to hold the switch state data. During phase 0, we drop the LD line, which asynchronously loads the switch state into the input registers. At that point, the H bit from the near chip becomes immediately available, so in phase 1 we suck that in and store it in the correct position of our holding register. In phase 2, we step the serial clock, which shifts all latch bits. The next bit then appears on the serial data inline, and in phase 3 we load that bit. This clock/load process continues until all data is read in, which takes 15 serial clock steps and 16 reads. From a logical perspective, we raise the serial clock on even phases except phase 0. We don't step the clock on phase 0 because that would be a bozo no-no, as simultaneous load and step operations would have unpredictable results. We then read in the stable data on odd phases. We only need 15 clocks anyway because the first bit becomes available immediately. At the end, the 5-bit phase counter wraps back to 0 and we start the whole cycle over again. Do we need configuration data this fast? Not really, but we'll need to share the serial clock and load lines with our external LED display, so we'll run it at this speed for now. We're not hurting any animals, and there's really no difference from a configuration register state perspective. Alright, let's code this up. I'm going to call this module a serializer because it's more generally what we're doing. For inputs, we'll need that 1 millisecond clock and the serial inline. For outputs, we have the serial clock and serial load lines that control the external shifters. We'll also need to export the switch state bits, so I'll add a 16-bit register. Those have to be registered as well because we're driving them from an always block. Next, we'll need that 5-bit phase counter. Then start an always block on the 1 millisecond clock. We drop the serial load line on phase 0 only. And raise the serial clock on even phases except phase 0. We know it's even when phase bit 0 is off. On odd phases, we suck in the stable serial data and drop that into the correct config bit slot. Here, if the low order bit is on, we know it's an odd phase, 1, 3, 5, etc. And here we're just dividing the phase number by 2 to get the proper data array index. Finally, we need to bump that phase counter. And that's it. Copy that signature domain and connect it up. We'll need a loose bus for that configuration data. Oh, I forgot the instance name. Before we hook up the individual configuration items, let's test this by shoving the upper 8 configuration data bits into the lower 2 digits of player 1's score display and the lower 8 bits into player 2's score. Need to temporarily disconnect those. I'll test each bit individually. You can see them turn on in the waveform and display. I apologize for the bad switch videos today. Didn't catch that until afterwards, and I'm not doing that trifecta again. Too lazy. Let's say we set the bonus level to 100 and the balls per plate of 5. Wrong bits. Better. Get rid of that test code. Revert that back. Now we can pick register bits and use those to drive our configuration items. First, I'm going to rearrange these so the original items are first. I'm going to change that name to cocktail model as a simple binary item and get rid of that define. That becomes a lot simpler. Now we can assign portions of config data appropriately. I'm just going in order. We do have 3 spare bits, and I would like to propose 3 additional configuration items. The first one is keep large paddle, which will not reduce the paddle size when hitting the back wall. This has been very convenient during testing and would be nice to have as a configurable item. The next one is max 9 credits, which will limit the credit accumulator to 9 instead of 15. This would help visually so you don't get into the hex digits on the credit display. It may confuse some people. And the last one will enable free play, which is self-explanatory. Oh, that's even simpler. Don't know what I was thinking. I know you saw that. Much better. Keeping the large paddle is easy and does not require any changes to the paddle module definition. We simply prohibit the input signal that tells the instance that the ball hit the top boundary. Max 9 credits is a little more complex, and we need to modify the credit module. Now there it is. I'll first pump those 2 configuration items into the credit instance, then add them to the module parameter list. We can't just change out the 193 for a 192 according to the switch, so we'll generate our own carryout based on our desired max limit. Carryout only asserts when up goes low, so I'll create a loose wire for up because it's used in 2 places. Now we can generate our own carryout signal based on the configuration setting. Use our loose up line, and we no longer need the carry out generated by the chip. Last thing we need to do is change the load value when we reach the limit. Remember that this is one less than the desired limit because the up clock takes a final step after the load is complete. We fix this anomaly on the retro board. Yeah, that should work. Free play is not too bad, and here we just force the 2+ credits line on when in free play. The 1+ credits line will automatically be turned on as well. This will enable both start game buttons. Now those values are decimal. That name doesn't match. Fix that. The Q latch gets set by the coinage instance when we drop coins. There it is. We're not dropping coins in free play mode, but we still need to set that latch for everything to work properly. The simplest thing to do without drastically modifying the coinage module is to get the coinage set line out separately, then drive the Q set output from either the coin set output or from either of the start game buttons when in free play. That should work. Oh, wrong name there. I'll run through a couple of test cases, load up some credits. Then switch between normal and show credits. That works. Turn on 2 credits per coin. That works. We can accumulate up to 15 credits. Enable max 9 credits. Now we can only keep up to 9. Anything over that is lost. Start a 2-player game and move to player 2. Turn on cocktail mode. That works too. Turn on free play. Both credit lights stay lit and either start button sets the operational latch. Set balls per play to 3. Game ends after 3 balls are used. Set the bonus level to 200. Annoying, but it works. Turn on the keep large paddle option. No shrinkage when we hit the back wall. Well, great, we added external switches and serializers and can now easily change configuration settings. I'm really missing that bling, however, so in the next video we'll add external LEDs. We've only got 1 pin left, so it should be fun. And yep, more serial stuff. I'll see you over there.